Okay, what we want to do today is finish discussing the design of the PEP-8 Arithmetic Logic Unit, the ALU. So last time we saw this overview. The ALU performs 16 different functions. And in figure 10.54 is a block diagram of the ALU, the Arithmetic Logic Unit. We see that how many data bits for A? 8. And how many data bits for B? Obviously 8. And how many bits for the result? 8. So those fat pipes represent 8 lines. Then we have the 4 lines coming in from the right that specify the function that the ALU is to perform. And we have a carry in that goes into the ALU. And then the 4 outputs besides the result are the N, Z out, V, and C out. Okay? And then we saw in figure 10.55, we looked at the 16 different functions that this ALU performs. Either A can go through straight, or we can do A plus B, or we can do A plus B plus Cn, etc., etc. And the last one was a little bit strange. What it did is it funneled A4, A5, A6, and A7 to the NZVC output lines. And then we looked at figure 10.56, which is a little bit lower level of abstraction, which means that more details become visible, because after all, abstraction is hiding details. And so here's more details. And so we saw that those 4 lines coming in from the ALU, coming into the ALU from the right, go into a 4x16 decoder. And what is always the output of a decoder when it's enabled? What is the output of a decoder? Just generally speaking, all of the what? All of the output lines are what? Except which is 1. Except for 1, which is 1. And how do we know which one is 1? Well, it depends on what the ALU, the number of that the ALU, the combination of the ALU number going in. Right? Is everybody with me on this? Okay. So the first 15 of those lines go into the computation unit, and the 16th line, which is number 15, goes into these 12 2-input multiplexers. And we resolved the little question, and we did say that it was indeed, this bottom box is indeed 12 2-input multiplexers as opposed to, what did we say, 10. Wait, is that the one where we had the little confusion of? Oh no, that was a different one. Sorry. Yeah, these are 12 2-input multiplexers. Yeah. Anyway, and then we see the individual lines for A and B on the top, and we see that A4, 5, 6, and 7 are tapped off, and they go into the NZVC of the bank of 12 2-input multiplexers. And we understand now that we have the N on the left group of the NVC, NZVC, corresponds to the N of the right group, NZVC, and depending on whether 15 is 1 or 0, one of those N's or the other will go to the N output. Now, do you remember how that worked? Okay. And then here, this describes which one. If line 15 is 1, then the result of the NZVC from the left are routed to the output. If line 15 is 0, the result from the right are routed to the output. And then, oh, this is the one. Figure 10.57 at the end of class last time was the one where we were trying to make sure in our minds that this is indeed 10 12-input OR gates as opposed to 12 10-input OR gates. Now, so let's think about that just another half a minute. So the fact that there are 10 OR gates, why are there 10 OR gates? Because each one of those units has how many outputs? Each one of those units, whether it's the A unit or the arithmetic unit or the logic unit 5 or the logic unit 14, each one of them has how many outputs? Has 10 outputs. And how many units are there? I think that's what was confusing. How many units are there? There's 12 instead of 16. But why is that? That's because the arithmetic unit takes the 4 possible.
Turns 4 into 1.
Yeah, they account for 4 of those. And look, you see then that the decoder, that these lines coming in from the right are the decoded lines, right? So we see then that lines 1, 2, 3, and 4 go into D, E, F, and G of the arithmetic unit. Are you with me? Is everybody with me on this? And of course, whenever each one of these units has an enable, right? Like you see the A unit has an enable. So if the 0 line coming in from the right into the enable unit of the A unit is 0, then that unit is what? Enabled or disabled? Disabled. It's disabled, and the outputs are going to be what? 0, regardless of anything else. Are you with me? So when that 0 line is 1, then the A unit is enabled. Right? And now, so what we're going to investigate now is how several of these units work. We're going to take a look at the A unit and the arithmetic unit, and we'll leave it as an exercise for the student to look at logic units 5 and 6 and on up. Right? So now, you guys, let's just think about it. In fact, I wonder if I gave you a little pop quiz now and you didn't look ahead to the next slide. Could you design the A unit? Let's just think about that for a minute. Could you? Do you think you could design the A unit? It's actually, I think you probably could. Because what does the A unit have to do? Well, how many lines does it have coming in from the top? It has 8. So you're going to have these 8 lines coming in. And what do you want to have come out? The result.
The exact same thing, right?
The exact same thing, because it passes A through. So it's just the exact same thing. But what about the V and the C? I think those can be zeros. Is that right? Let's go back and look at our table.
Yep,
if we look at, here, let's go back to figure 10.55. If we look at figure 10.55, it says if the ALU control is 0, that sends A through, and what it does is the status bits are N and Z, and then the V and the C out are 0 and 0. So we can just make those 0. Okay, so let's go back to this figure 10.57 and contemplate again. How would you do that?
8 OR gates.
Oh, close. He said 8 OR gates, but...
Why would you need any gates?
Because of the enable. We have an enable input. What does the enable input have to do?
AND gates.
Yes, 8 AND gates, and then what does that enable have to do? Either lets them go through or not. Okay, so does everybody see how that would work? Mm-hmm. Okay, and the output would be what? Or the result, those 8 results would be the 8 outputs of the what?
Of the 8 AND.
Of the 8 AND gates. The enable would, and one of the, well, it's hard to say in words, but, so each one of the 8 inputs would go to one of the AND gates, right? Spit out and go, and then the enable would feed into the other inputs of all the ANDs, right? And then the V and the C are what?
Yeah.
And so we could just ground those, like on your lab, make them zeros. And that would be it. And so here, did we do it right? Figure 10.58. There's the A unit.
Cool.
Now, are you with me?
One level.
I tell you, see what good digital circuit designers we are now? Mm-hmm. We can make this stuff. All just from our knowledge of Boolean algebra and, which is based on formal methods, which is all, and now we can put together things to add and send A through and enable. It's all just, you guys look, it's not hard. It's just plumbing. You see what I'm saying? It's like water going through a pipe, and you switch it on and you take it from here and it needs to come over here, and it's just stuff going through. It's just signals going through. That's all it is. Yeah? And it's all logic. It's all based on logic. Now comes the harder one. Now let's take a look at the arithmetic unit. Now let's consider what goes into making an arithmetic unit. Now, instead of just having an A, what do we have? We have 8 lines coming in for A, but we also have what? 8 lines coming in for B, right? And now, this is an arithmetic unit. Now, what 4 things does the arithmetic unit have to do? Let's go back and take a look at them in figure 10.55. It has to be able to do what?
Add A plus
Yeah, A plus B. It has to do what? So that's one thing. If it's 1, it has to do A plus B. It has to do 4 things. It has to either do A plus B or what? A plus B plus C in, or it has to do A plus
complement
B bar plus 1, or it has to do what? A plus B bar plus C in. It has to do one of those 4 things, right? So you know at its heart, what's it going to be? It's going to be very similar to our what? To the adder subtractor, right?
Right.
In fact, it's going to be just a little bit more complicated than the adder subtractor. It's going to be, because what did the adder subtractor have? It just had one sub.
Right.
But now instead of having instead of having a sub, what do we have? We have to have it be able to do 4 things. But they're all based on plus with inverting. Are you with me? Is everybody with me on this? So look, it's really not that bad. Are you ready for this? Drum roll. Here comes figure 10.59. All right. Now there are 8 full adders. All right. So we have ... here. Are you with me? Is everybody clear? So each one of these boxes in the middle, this is a row of 8 full adders. And just like we had with our adder subtractor, we have for each full adder coming in from the top that B goes through, we have a set of what? What gates does the B go through?
XOR.
Yeah, exclusive OR gates. Yeah, XOR gates. So we have XOR gates. And the XOR gates, again, act as what? Selective inverters. So we can either invert we can either invert B or not. So let's go back to our table and see which ones. See, so we see that when the ALU control is 0, 0, 0, 1, we don't invert B. When it's 0, 0, 1, 0, we don't invert B. When it's 0, 0, 1, 1, we do invert B and we add 1. And when it's 0, 1, 0, 0, we do invert B and we have to also add C in. So it's the second 2 ones where we have to turn on those selective inverters. Are you with me? Simple enough to understand? Are we good? I think it's pretty good. So now, what I've done here is I'm leaving it as an exercise for the student to design this little black box in the upper right corner. Okay? And we can think about what it has. So, but does everybody understand? Does everybody understand like the overall principle of operation of this circuit? What we have here is coming in from the left, we have a C in, and then we have our D, E, F, and G. Are you with me? Let's go back and take a look. Let's make sure that we understand the input. Let's make sure we understand where this C, N, D, E, F, and G are coming from. Let's go back to figure 10.57. You see, that's the Cn coming from here. Are you with me? And then this is the D, the 1 is the D, the 2 is the E, the 3 is the F, and the 4 is the G. So does everybody understand that when D is 1, that's when we're selecting what? Well, that's when we're selecting it to do what?
A plus B.
A plus B. When E is 1, that's when we're selecting it to do what?
A plus B plus C.
A plus B plus Cn. Are you with me? And so on. Are you with me? And then we have this Cn is also coming in, right? And then we have the A and the B coming in. That's all the inputs we have coming in. Okay? So here's what you should be able to do. So therefore, can you write a truth table for this? There's 2 outputs. There's a sub output and a C output. So could you write a truth table for this? I think one of your exercises is to write a truth table for this box. Could you write a truth table for that? I mean, does everybody understand what it needs to do? Based on this, you still have a question about how to write the truth table for this? Okay, do you understand that if Cn is, if D is 1, then what does if D is 1 and the rest of these are 0, then what does this output, if D is 1, what should sub be?
0.
Yeah. So you just did one entry of the truth table. If D is 1, sub has to be 0. And if E is 1, what does sub have to be?
1. No, 0 as well.
0. And if F is 1, what does sub have to be?
1.
1. And if G is 1, sub has to be 1, because we need to invert B.
They'll never be 1 at the same time, right?
That's a very good observation. The observation is that only one of D, E, F, and G can be 1 at one time. But it's also possible for them to all be 0.
Yeah. Which is why you have...
Yes. So because if they are all 0, yeah, that's a good point. Now let's understand the principle of operation of yeah. And so what it does is it just goes through this set of 8, it disables the AND gates for the output. Is that slick? You guys are good. We understand how we can read logic diagrams to build these moderately complex functions. Are we good? Mm-hmm. That is cool. So what it does then? So this OR gate. If these are all, if just one of these is 1, then what happens? This bank of AND gates are all enabled, and it functions as usual. The signal just goes through. But if they're all zeros, then they're all disabled, and nothing goes. 0 comes out regardless of what the input is. So notice that it's always calculating. All these circuits are all... Do you realize that what's literally happening in the circuit is that all 16 of those functions are actually doing their thing, but some of them are being blocked from getting through. That's basically how it works. Are you with me? Because of the concept of the enabling.
Isn't that inefficient?
Well, but it's fast. Because they're all 16 doing their thing at once, and then whichever one we want to have it do it, we just let that one through. And because they're all happening at the same time, it's not. Do you see what I'm saying?
It's literally concurrent.
It's literally concurrent.
Okay.
That is a good point. That's a good observation. So what we would have to do to determine the performance of the ALU would be to detect, if I gave you an assignment to write, you wouldn't want me to do this, to write all the individual AND and OR gates of the whole ALU. Expand this block diagram out, and expand this one out, and expand this out, and have it just be all gates. Can you imagine how many gates there would be? And then you would have to do what? Trace through and find the what? Trace through and find the what?
Gate delay.
The longest path from an input to a what? An output in the number of gates. And that would be the gate delay, and that would be the performance of the ALU.
And then you would make that an AND OR.
Oh, and the whole thing. Yeah, the whole thing could be made a 2-level AND OR. But man, that would be humongous. I mean, yeah.
Let's do it.
Well, you want to do that? Yeah. Oh, that would be a nice assignment. Programming. I could do that for the final. Take-home final. 2-level AND OR. 2-level AND OR of the ALU. But you can imagine. I'm glad we know enough about this to where we can joke about it. That's pretty cool. Okay, and so now I think that's it. Are there any more questions about how this works? And let me see, what about the C? Oh, and notice that we already know how the C and the V work, because that's just, we have the exclusive, to get the V bit, it's the exclusive OR between the last stage and the penultimate stage, right? So that's how the V bit works whenever you do an addition, right? And the C bit is the C out of the last stage. Yeah? And then it's an exercise for the student to do the truth table and you'll actually design. You can put the gates in here. All right? And that's it. Oh, and then also it's an exercise for the student to do, these other logic. But look, how would you do A and B? Here, let's think about how you would do logic unit 5. What would you do? Let's just think of it. Let's just do this one in our head. How about logic unit 5? What does logic unit 5 do? A and B. So
Spin AND gate. It'd be 8 ANDs.
it'd be 8 AND gates. How many inputs for each AND gate?
3.
You might think 2, one for A and one for B, but, and the enable. It'd just be a bank of AND gates with an enable. So it'd be a group of what? 8?
3 input ANDs.
8 3-input ANDs, and do V and C, I think V and C are also 0 in that case, right?
I would assume so.
Let's check it on the table. Figure 10.55, A and B, yeah, the V and the C bits are 0, specified to be 0 anyway. Yeah? And then what about the V? Wait, what did we say? The V and the C. We don't have to calculate the N. Right, we don't have to calculate the N bit and the Z bit. That's calculated where? That's calculated in figure 10.56 outside the computation unit. Right? So we don't have to worry about the N bit and the Z bit. Is everybody clear on this? All right. Now, one more thing. You guys have done some homeworks where we have like, if you have what did I have you do? 2 8-input multiplexers and make a 16-input multiplexer?
Yeah.
Yeah, so I have 2 8-input multiplexers, you make 16-bit multiplexers. Okay, so now, and then I think you also had one to do it for a binary decoder, right? So you do and that's very common. It's very common in hardware design to have, to make a device that operates the same way as a smaller device by combining, usually you combine them in 2s or 4s, to have it do more at the same time by using several of the smaller devices. Well, you guys, do you remember in PEP 8 how big the accumulator is? No. Do you guys remember how big the accumulator is in PEP 8?
It's a word.
Which is how many bytes?
16.
No. 2 bytes.
Oh, sorry.
Which is how many bits?
Yeah, I meant
16 bits. Yeah, I know you. It's 16 bits, right? So it's 2 bytes. That's the accumulator, right? Now, on the other hand, this ALU can only add how many bits at a time? 8. Are you with me? So you guys, here's the question. In the same way that you used 2 8-input multiplexers to make one 16-input multiplexers, you could do what? You could use 2 ALUs, 2 8-bit ALUs to make a what? 16-bit ALU. You could do that. Because the ALU has what? It has a C in and also has a C out. Are you with me? Now, here's what we're going to do. So that's one possibility, is to actually physically duplicate the ALU and hook them together in slices. And many ALU chips in the early days, of course nowadays, the whole ALU and the whole CPU is all on one chip. In the early days, they used to have ALU chips, and they were slices. Like you could buy a 4-bit ALU, and then you could put like 4 of them together to make a 16-bit ALU and put the C out of one to the C in of the next, like that. Are you with me? And they actually used to build the chips like that. But the concept, no matter how much integration we have, the concept is the same. Now, what we're going to do, the way the PEP8 hardware is built, what we're going to do is we're going to have one ALU, and this ALU can only add 8-bit integers. So in order to add a 16-bit integer, what it does is it uses the same ALU, but it does first the low order byte, and then it does the high order byte. It does the low order byte, and it saves the C out and the V and the Z out and the N to be used for the high order byte. So it actually takes more than one. Do you see what I'm saying? It takes more time. This is a space-time trade-off. If we had two ALUs together, we could do 16 bits at one time. But if we only have one ALU, we can still do it. We'll just do the low order one first, and then we'll do the high order one second. Now, does everybody see the concept there? Are you with me on this? And what we'll do is we will run the low order arithmetic. We will run the low order through and save the C and the V and the Z out and the N, and then we'll use those. We'll use the C in for the next one, for the next order, higher order. All right. So here's how that works. Well, let's go back to our table. So now tell me, how would you add two numbers? Like, so here, addition. Addition of 16-bit quantities. So suppose we wanted to do this. Suppose A is 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0. And B is 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1. I'm just making these up. All right? So how would we add this using this? This is a real simple example. How do we add using our 4 functions that we have with the ALU? What's the first thing we would do? Well, we would take, what would we do? Yeah, what we would do is we would add these using which function?
ALU1.
Yeah, we would do this using function 1, because that would be A plus B, and there's no carry in.
Right.
And then we would save the carry out,
Right.
and then we would do what?
Function 2.
And then we would do function 2,
And get the carry out.
and take the carry out from this, and do function 2, because that's A plus B plus carry in. All right, so does everybody see? I don't want to do this in binary, but you can see how to do that. Is everybody, that's pretty straightforward. Does everybody see how to do that? How you would do that? So that's how we do addition. So the two, you see we use function 1 and function 2 of the ALU to add 16-bit quantities. And we do the low order byte first, and then we do the high order byte. Is everybody with me on this? Yeah, question?
And as you're doing it, it just stores them to memory?
Yeah, there's another, the NZVC bits you'll see in the next chapter. We'll see in a later chapter that the NZVC bits have to be stored. Yeah, the output has to be stored and then used as the C. The C out has to be stored and then used as the C in for the next one.
And the results are all stored as you're going?
And the results are stored, yeah, somewhere else, actually in a register in the CPU. That's where they're going to be.
Oh, not in memory?
No. All of this is in the CPU, not in memory. The ALU is in the CPU. So there's going to be there's banks of registers in the CPU, and it's going to go into a register of the CPU.
Okay.
That's where the result is going to go, looking ahead.
Okay.
But that's the way to visualize it. Are you with me? Is everybody clear? So that's how we do addition of 16-bit quantities. Now, so we use functions 1 and 2 from our table in figure 10.55. But now, how about we do subtraction? Now this subtraction is a little bit more complicated. So let's do this. Let's do 259 minus 261. Let's do 259 minus 261. So if you work this out, 259, here's 259. I'm going to write it out, see if you agree. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0.
0, 0, 1, 1.
Oh, good. 0, 0, 1, 1. Man, you know your binary. Okay? So this part right here, on the left, we're going to label this A high, and this we're going to label A low. Okay? So this is the high order byte, and this is the low order byte. Are we good? And then, and you can see that this is 259 because it's 1 plus 2, 4, 8, 16, 32, 64, 128, 256 plus 3 is 259, right? Is everybody good? And I will tell you that 261, and what is 261? That's 259. Now what is 261? 261 is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1. Wow, that's cool. All right? And this we're going to call what? And this we're going to call what? B low. So this one is going to be B high. And this is B low. All right? B low. Yeah, yeah. All right. Now, you guys, let's pause for a minute here. I forgot to show this slide a minute ago. 10.60a is how we do the A plus B on the low order first, and then the C out from that goes to the C-in of the next one, and then that's A plus B plus C-in. So that gives the sum high and the sum low, right? And now, and so as you anticipated, what happens is what we'll do is we do, now why do we do A plus B bar plus 1? Because we are negating this, right? So check this out. So let's do the low order. So here, let's do the low order.
I'm wondering why you would ever do this.
Yeah. Isn't that slick how that works? There's exactly two different functions, one for addition.
Yeah, I was like, I don't.
Yeah. Why have that? It seems weird, but now you can see why. Okay, so we do the low order first. So let's do the low order. The low order is going to be, we add what? 0, 0, 0, 0, 0, 0, 1, 1. So here's 0, 0, 0, 0, 0, 0, 1, 1, and then 0, 0, 0, 0, 0, 1, 0, 1. 0, 0, 0, 0, 0, 1, 0, 1. Oh, sorry. This, to do the low order, it's what? A plus what? B bar
Yeah.
plus 1. So here's so this one is the A. Now what's the B bar?
1, 1, 1.
The B bar would be 1, 1, 1, 1.
1, 0,
1, 0, 1, 0, right? 1, 1, 1, 1, 1, 0, 1, 0, and then an extra what?
1.
An extra 1. So here it does this. So can we do this?
0.
0, carry your what?
1.
1,
Carry the 1.
carry the 1,
1.
1, carry the 0.
Carry the 1. Oh, no.
No. Now this one is what?
1.
1. Now this one is
And they're all
1, 1, 1, 1, right? And C equals what?
0.
0. Are you with me?
Mm-hmm.
And so that's the low order, and then the high order. So that's now the high order. Now, so what do we do with the high order? It's A plus what? B bar plus Cn. So now, so this is A low, B bar low. This is, so our, oh rats, I don't, do I have room? Yeah, high order. So now what is our high order? A plus B bar plus Cn. So here's A, and here's B bar, and here's and our Cn. So now what's our A? 0, 0, 0, 0, 0, 0, 0, 1, is that right? 0, 0, 0, 0, 0, 0, 0, 1, and then B bar is what? 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, and our Cn was what? It's this 0 which we saved from the previous one. So that's a 0. So now what is this? 1, 1, 1, 1. Is that right? 1, 1, 1, 1. Did we do that right? And C is what?
No.
And V is what? I think it's 0.
Yeah, V0.
V is 0, right? Overflow for signed quantities. V is overflow for signed quantities. So what is the result? So the result is stringing them together, right? So the result then is the high order is 1, 1, 1, 1, 1, 1, 1, 1, and then what? 1, 1, 1, 1, 1, 1, 1, 0. Are you with me? What number is this? This is binary. What number is this?
Oh, -2.
It's -2. Well, what is 259 minus 261?
-2.
-2. I rest my case. Are we good? Let's focus over here. Now what would happen if we did, just to show, what would happen if we did, instead of 259 minus 261, what would happen if we did 261 minus 259? So, example, 261 minus 259. Now is it still going to work? So what's the low order? The low order would be what?
0, 0, 0, 0, 0, 1, 0, 1.
0, 1, 0, 1. So here's this is our A low, right? And then the B bar low would be what?
0, 0, 0, 0, 0, 0, 1, 1.
B bar? I don't think so.
Oh, B bar, sorry.
B-
All one.
Yeah.
Opposite of that.
So it'd be what?
1, 1, 1,
1, 1, 1, 1,
0, 0.
1, 1, 0, 0. And then, but then that function that we're doing is what? We have to do what?
Add a 1.
Add a 1. Is everybody clear? So what's 1 plus 0 plus 1? 0 carry the 1. 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 And what comes out?
C equals 1.
C equals 1. Is everybody good? And then the high order, so that's the low order. And then the high order is what? So the high order is going to be 0, 0, 0, 0, 0, 0, 0, 1, and that's our A high.
And then B bar high
And then B bar high
is 1, 1, 1, 1, 1, 0.
is 1, 1, 1, 1, 1, 1, 1, 0. And then, but this time, what happens?
Cn.
We have our Cn. Oh, I'll put it over here. So here's our Cn. Okay? And now when we do this addition, what do we get? 1 plus 0 plus 1. 0 carry the 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 1. And now what do we have?
C equals 1.
C equals 1. And what about V? Tisk, tisk.
Equals 0.
Equals 0. Yeah? And what number is this? So now what is the result? So the result is what? The high order, it's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, binary, which equals what? 2 decimal. And see, it worked. Proof by example. Just kidding.
So if you were doing, for example, 250, or overflow bit would only work if the two numbers added or subtracted together were either below or above
Right.
what they were able
If you added two positives and you got a negative, you got a 1 in the sign bit. And that exclusive OR gate would be you only need the V bit is only relevant in the high order operation. Notice that we didn't use the V bit in going from here to here. We didn't need to store it. Does everybody see how that worked? Oh, look, I said draw the truth table. It's left as an exercise for the student to draw the truth table, but I lied. Sorry, defect of my character. I don't always tell the truth. So figure 10.61 is actually the truth table for the sub and the C outputs of that circuit. Are you with me? So here, if the function is a plus b, and if d, e, f, and g are 1, 0, 0, 1, 0, 0, 0, then sub should be 0 and c should be 0. If it's a, okay, the function is a plus b plus cn, 0, 1, 0, 0, etc. Yeah? Are we good?
Oh, I was going to do like
Okay, now that brings us to the end of this chapter, and we do have a few minutes left, and the next topic is so important, and I think we can get some really interesting insight, even though we have just a few minutes. As usual, I always wish that we had covered more than we actually do, but that's life. But I think we can get some good concepts in here. So, are you ready? Now, we will start by asking, what is the characteristic of a combinational circuit? The output depends only on the input. So with a sequential circuit, obviously, why were we making such a big deal out of it? The output's not going to depend only on the input. So my question is, what's it going to depend on also? Not only the input, but what? The phase of the moon, the weather. What's it going to depend on? What else could it depend on?
Nothing?
Well, it's got to depend on something. Electricity. Starts with an S. What is the list of variables and their values? Oh, sequence. What's the list of variables and their values? It's going to depend on the state. The circuit is going to have a state that's going to persist. Are you with me? And the output is going to depend not only on the input, but also the state that the circuit is in. Does everybody kind of like see the concept? So, combinational circuit, the output depends only on the input. Sequential circuit has a state. The output depends not only on the input, but also on the state that the circuit is in. So now here's what's amazing about sequential circuits, you guys. What did we say? If you were stranded on a desert island and you only had one kind of gate, if you only had a what? NAND gate, you could do what? You could build any circuit you wanted. Right? Well, guess what? In order to have circuits that have state, we don't need any new gates. There is no new device. If you had that bunch of NAND gates, you could build sequential circuits as well as combinational circuits. The only difference is how you hook them up. Now, have you noticed in all the problems that you've done so far, all the exercises and all the labs that you've done so far, how did you hook up these gates? The output of one gate always went to the what? To the input of another gate. And that output always went to the input of another gate. But not only that, not only does the output always go to an input, but the input, the output of that gate never did do what? Never did go back the output and go to the input of one that was earlier in the sequence.
Didn't have any loops.
Right. That kind of a connection is called a feedback connection. Okay? So a sequential circuit is constructed from standard gates, but with one or more feedback connections. Now, there's two things that can happen when you have a feedback connection. If you take a wire and you put it back to one that's earlier on in the sequence, there's two things that can happen. You can either produce an unstable circuit, an unstable state, which changes rapidly and never settles down, or you can have a stable state, in which case it will eventually settle down and have just one value. Now here on this next, I think we can show you. We can illustrate this with this figure 11.1. Now watch this. I'm going to repeat this figure on the board here. You know, do you remember in the lab the hex inverter chip? Well, if you power that up, and there were six inverters in one chip, right? You could go from pin 2 to 3, or I forget the pin numbers, but you could hook this one to this one, and this one to this one, and this one to this, and then you could take this one and hook it back to this one, right? What do you suppose would happen if you put this one on the light? If you put this on the light?
It blink.
Ooh, it would blink.
Yeah.
You're right. It would blink. And why is that? That's because if there's a 1 here, one gate delay later, what will happen here? There'll be a 0 here, and 1 gate delay later, what will happen here? There'll be a 1 here, and 1 gate delay later, there'll be a what?
0.
A 0 here. But almost instantaneously, namely at the speed of light, this would make this what? A 0. And then 1 gate delay later, this would be what? 1. And 1 gate delay later, this would be 0. And then 1 gate delay later, this would be what? 1. But then, boom, boom, boom. So therefore, if you looked at this in time, so if you looked at this. So if this is time, what would happen is, and you measured the voltage here, it would do this. And furthermore, what did we calculate in this circuit? How long would it take to go from, this is 1 and this is 0, right? So here's 1, here's 0. Are you with me on this?
Right.
And this is time. So, and how long did we say it would stay up here? 3 gate delays, 3 T sub G. And actually, you say it would flicker so fast that you couldn't see the flicker because your eye can't respond that fast. And so the light would be like dimmed at half the intensity because it'd be on half the time and off half the time. But you couldn't see it flicker, so it'd be dim light. That's what it would do.
Interesting.
Yeah, you can try it. Next time we do the lab, you can try that. Yeah.
Is that how blinking Christmas lights work?
No,
Oh.
they don't have lights. Blinking Christmas lights do not have gates in them. Sorry. Okay, now
What does that say? 3TG?
gate delays. TG is the gate delay.
What's the thing on the sides of them?
Oh, that was supposed to be an arrow. That was, my drawing is not very clear. Okay, so.
Oh, got it.
Yeah, sorry. So, are you with me? So every third, and furthermore, it'd be like 5 gate delays if you had 5 of these. But look, if you have just 2 of these, watch this. If you have just 2 of these and you hook this back and you feed it back to here, watch this. Now watch this. If this is 0, Then one gate delay later, what will this be? 1. And one gate delay later, what will this be?
0.
0, but now this is 0. Nothing would change. Indefinitely, forever, it would stay like this. But wait a minute, you ask. What are you going to ask? But now what are you going to ask?
What's that for?
No, 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 no. There's another question that you should be asking right now. I said, how did we start this whole thing out? We said, what did we say? If what? If this is 0. Yeah, but what if this were 1? Then what would happen? One gate delay later, what would happen?
0.
This would be, and one gate delay later, what would this be? 1. But this is consistent with this one. So it would do what? Stay in this state forever. So the question is, if you hook this up in the lab, will it be in this state or will it be in this state? So here's what happens. You hook it up in the lab and you turn the power on, and all things being equal, if there's no little perturbations. No, 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 no. Because half the time it'll come up in this state, half the time it'll come up in this state. You can't predict.
Cool.
But this is stable. In other words, once it gets in its state, it will stay that state forever as long as the power stays on.
Oh. So
Are you with me? Whatever state it's in.
You could turn
In
off
fact,
and
in fact,
turn
you could tap. You could actually take one of those leads, and put it in power. And you could, if you tap, if it's in this 0 state here, and you put it in power, and you tap it here, it'll actually change it to the other state. And if you put it on ground, if it's in the 1 state, and you put it on ground, and you tap that wire here, boom, it'll actually flip the state. But there's no way to tell, if you power it up, which state it's going to be in.
that's pretty cool.
It is cool. Is this neat? I leave you with.
This one.
Well, there are other. It depends. It's like, is the leaf going to fall? There's so many. Things aren't always equal. Is the leaf going to fall to the left or to the right with no breeze? A feather. There's little things. It's like chaos theory. Some little thing will make it go one way or the other, and then it will just continue to go that way. You see what I mean? But we can't predict which way it is. And furthermore, there might be some sort of asymmetries in the way the circuit's built, so it might always come up the same way. But we can't predict which way it's going to come up until we do it a few times or something like that. Are you with me? But there's no way to predict. See? But this is stable, this is unstable, this one's unstable. Pretty neat, huh? We're going to continue this on Thursday. See you later.